Hello, my name is Brennan Beam, and I'm a hydraulic engineer at HEC. In this lecture, I'm going to talk about using 2D hydraulics in FDA 1.4. To begin, I want to make sure that everybody understands where the hydraulics I'm talking about fit into the overall FDA compute. Then we're going to move into how 1D hydraulics were processed in FDA, and how we're going to now process 2D hydraulics in a compatible way. And then finally, I'm going to do a little overview of the tutorial, whose link is going to be available at the end of this lecture. First, we have our 4-panel FDA compute. We've got flow frequency in the top right, the stage flow relationship in the top left. That's the first time we see hydraulics in the FDA compute. But we have hydraulics again that are involved with computing the stage damage relationship. And that's really where I'm focused on today. The rating curve, or the flow stage relationship in the top left there, is really important is representative of the index point, whereas in the stage damage relationship, hydraulics are involved with calculating damages at every structure. And we'll explain that a little bit more here. That stage damage relationship is an aggregated curve that represents your entire structure inventory for that reach and all of your profiles. So each hydraulic profile represents a stage on your stage damage curve. More frequent events are going to have lower stages. Less frequent events are going to have the higher stages. And for each one of those profiles, we're going to calculate damages at all of the structures and sum them up to create this curve. And all those summed damages make the point on the curve. When we go through them all, we get to fill that curve out. Sampling with uncertainty in Monte Carlo, we create the uncertainty bands around it. But anyway, these are the hydraulics that get really tricky with using 2D rather than 1D. In the end, for either 1D or 2D, we essentially want to communicate the information in this table to FDA. We want to tell FDA for every profile what is the depth at each of our structures. Now that I've established the goal in creating that conceptual table, I want to talk a little bit to any non-hydraulic engineers in the room about what 1D hydraulics are, and then how FDA uses those 1D hydraulics. So 1D stands for one-dimensional, and that dimension is along the streamline. So water can only flow along the streamline. The key component to a one-dimensional hydraulic model is the cross-section. A cross-section is a line that we force perpendicular across the flow path, and we always assume that water surface across that line is constant. What this lets us do when we report out results from a 1D model, we report out a table of the cross-sections and their related water surface elevations. And for all of our structures and our structure inventory, as long as we know at what river station that structure lines up to, is perpendicular to, we can interpolate between the bounding cross-sections to find that depth. When we look at that from the side, we get something like this. Here I've got a water surface profile with just 2 profiles on it and 3 cross-sections, just keeping it real simple. And then in our structure inventory, we've got 2 structures. One falls right on the cross-section. It's pretty easy for us to get that guy's depth if we want it, because we know the first floor elevation of that structure. We know the water surface elevation of the cross-section it sits on, so we can get its depth. And then for the second structure, for structure number 2, even though he's not on a cross-section, we know the water surface elevations of the one just below him and the one just above him, and we know his station, so we can interpolate to find that value. And when I say we, really I mean FDA. FDA can do that interpolation for us. 2D hydraulics are a little bit different than 1D. 2D allows water to move on a 2-dimensional plane rather than in a straight line going downstream like a 1D model. Importantly, it means we have abandoned the concept of a cross-section. Now we have grid cells that flow gets to move around on. So when we report out results from a 2D model, we typically report out a depth grid, a raster file of depths or water surface elevations. In the case of our tutorial, we're going to be using depths. To communicate this new type of information to FDA, we're going to have to find a way to transform it back into a lookup table. And we're going to need to make sure that at no point does FDA ever have to interpolate between 2 points, because we don't have cross sections anymore. There's no longer a way to linearly interpolate between results to find answers. The way we're going to do that is to sample the water surface elevation at every point in the structure inventory. So instead of having some number of structures and some number of cross sections, we're going to create a one-to-one mapping between entries in the water surface profile and entries in the structure inventory. So FDA can just look at the station of the structure, go look it up in the table, and get its depth. With all that background established, I want to give a little introduction to the tutorial itself. The link is up there at the top of this slide. Our first step is going to be extract the data from depth grids using QGIS. You'll have a set of example hydraulic results for West Sacramento that you'll get to pull data off of. Once we get that done, we're going to copy and paste that table of results into Excel, where hopefully folks who are less used to GIS can be a little more comfortable, and we're going to do some pre-processing there. Once we've got our data kind of clean and looking like we want it, we're going to create an ASCII import file off of a template that can be imported right into FDA, so we don't need to mess with entering into the forms directly there without copy-paste. And then finally, once that template's all filled out, we can import it into an FDA study. So our first step here, we're going to extract the data from the depth grids. You'll be provided with hydraulic results in the native format they came out of RAS as depth grids. You'll load those grids into QGIS. You're going to use a tool in QGIS to sample raster values from each of those results using a structure inventory shapefile. After completing that step, instead of having 8 raster results, you'll have 8 shapefile results that have the structure inventory information and a depth value from whatever raster it sampled. So the next step will be joining those shapefiles into one, because we want all those profile values in a single shapefile, and then we're going to open that attribute table and we're going to copy it into Excel. Now that we have our data in Excel, we need to fill out any empty cells. Empty cells represent dry structures. Unlike 1D data, this method of incorporating 2D data doesn't give us any indication of how close to flooding a structure is, so we have to make some assumptions, keeping in mind that during the actual compute, FDA will be interpolating between these points. For the structure on the table, we know it does not get wet until somewhere between the 10 and 25-year event. We enter a -2 as the depth for the 10-year event because that's the lowest value on a depth damage curve for most occupancy types. So anything larger than the 10-year event is going to start seeing some damages, and anything smaller will see none. The smaller events are assigned an arbitrarily large negative number of -9 to ensure that those events and anything in between will never see any damages. Once that's complete, we need to validate that our profiles are monotonically increasing for the structure. When I say monotonically increasing, I mean to say that as the return interval gets larger, so as we go from the 25-year to the 500-year, the depths that structure sees are getting larger. If that's not the case, FDA is going to throw a fit. And also, you should be suspect of your hydraulic data or the sampling that went into it. So at that point, it would be good to bring on your hydraulic engineer to review the results with you and ensure that they're valid. The final step here with the pre-processing is to name your stations. In the end, we're going to have your structure inventory as a table in FDA and your water surface profile as a table in FDA. And we need to make sure that we name our stations in the water surface profile and map them correctly to all our structures in the structure inventory. Now that all our data is clean and ready to go, we're going to download the stage discharge ASCII import file template from the Confluence tutorial page, and we're going to fill it out. So you've got to go through and add your water surface profile name, your description, your plan, and all of your data that we've just spent all this time generating for this process. The trick here is you're also going to need to include here your index point. And your index point is treated a little bit different than any of your other points. The big thing, it needs to use elevation rather than depth. So you can see here the index point has an invert of 10, stages in the 30s. Those look so drastically different than every other stage in that water surface profile because the others are depths and this is an elevation. You're also going to have to fill out your flows. And flow really only matters for your index point. So work with your hydraulic engineers to get the flow at that index point for each of these profiles. But when you're putting it into this form, feel free to just enter the correct values for your index point and drag the rest down. FDA is not going to use those flow values, but it does need them in there for the import. Finally, you're going to go ahead and import your ASCII file into FDA. The tutorial will guide you through how to do that in all of this process. But the only snag here that you might get tripped up on, once you're imported into FDA, you need to assign your study damage reaches, which is where you identify the upstream and downstream stations, which are arbitrary stations now, but you need to make sure that the range you give encompasses all of your station numbers. Your bank ought to be set to both, and identify your index location. And that's the end of this lecture. I hope this gives you a good base to kind of tackle the tutorial with. The link to the tutorial is at the top of this page. Please feel free to ask questions as you go through it in the class. And if you ever return to this tutorial to apply it to your own project, please post questions on Discourse, questions, suggestions, any comments. We're happy to hear back from you and help you make use of this tool. In the meantime, happy modeling and good luck.